Hey everyone, so welcome to your first higher level topic. This should be fun for everyone. Today we're going to talk about diffraction and interference, two things that you've seen already, but we're going to do them in a lot more detail and we're going to calculate things. And I know that everybody loves to calculate things, so let me just show you what we're going to calculate exactly. This thing here is not a cigar, it's supposed to be a flashlight or a laser or something that's emitting some light. That's, goes a little bit like this. And then what we want to know is what happens if I put some obstacle here, like a wall. And this wall can have an opening or several, and the openings can be small or big or what. And we want to know what happens depending on the size of the opening and the number of openings that we put in here. And then after this, I put a little screen at the end, and I want to know what pattern this light that goes through the opening or openings will do on the screen. So again, all we want to know is I have some source of light, I shine it through one or more openings, and I look at the pattern on the screen. And we want to learn how to predict what pattern we're going to see, just by looking at the type of light that is being emitted and the opening here. Okay, so the first thing that we need to do is to revise the principle of superposition, which we have already talked about when we were doing standard level. And what it said is that if I have two waves, so wave number one, wave number two, that are in the same position in space, then the displacements are going to add up. So for example, if I put them like this, I'm going to get a wave that will look twice as big as the other two, because each one of these points just adds up. So the height will just go up. We call this constructive interference because the waves help to build each other. Now, another possibility is if I take one of these waves and I put it like this. And what happens then is that because these two things again add up, so this and this is adding up, this and this is adding up, what I get is really a wave that's flat, like this, right? And this is called destructive interference. And this means that the waves cancel each other out because the displacements are adding up and they're opposite. Now, what we need to remember are the conditions for destructive and constructive interference. Now, here we have constructive interference when the difference between the paths of the waves, and remember the path of the wave is just how much it moves, right? So this wave starts here, and then it's moving this way. And after a while, it will have moved a certain amount. So for example, after this, it's moved by half a wavelength, and after this, it's moved by one wavelength, and then by another half a wavelength, and then by another wavelength. So the distance that the wave has moved is just the path that it has moved. And we call the path difference simply the difference between how much this way has moved and how much this way has moved. So let's look at the path difference of these things. So again, here we see that if the path difference is 0, because these two have moved exactly the same amount, then we get constructive interference. So for constructive interference, we get path difference of 0, but we also get it if I keep moving this thing to the right. We also get it when the path difference is one wavelength. So 0, one wavelength. And if I keep moving this to the right, I will also get constructive interference when I have moved by one and two wavelengths. So 0, one wavelength, two wavelength. And it's easy to see that I'm going to get constructive interference for 0, one wavelength, two wavelengths, three wavelengths, and so on. So for any integer number of wavelengths. And that's the condition for constructive interference, and we're going to have to remember this for when I start deriving things, when we look at the path difference between two waves that come from different places. Now, apart from this, we can also get destructive interference. And what is that? Well, all we need to do is, instead of putting it here, when I move this much, we can see that these two waves cancel out. So this and this cancels out, this and this cancels out, so I'm going to get a straight line. In this case, the path difference is this much, which is exactly half a wavelength, because this is a wavelength, this is half of it. So we have destructive interference for half a wavelength. And what else? Well, if I keep moving this to the right, now I have constructive, now I have destructive. So let's see how far this is. This is 1 wavelength and a half. So 3/2 of a wavelength. 3 lambda over 2. And I can keep doing this and moving this further, and in this case I'm going to have 2 wavelengths and a half. So it's always like 1 wavelength and a half, 2 wavelengths and a half, 3 wavelengths and a half, and so on. So 2 wavelengths and a half are 5 lambda over 2. So you also see a pattern here, right? This 1, 3, 5, 7, and so on. So you can say it's an even number of wavelengths, sorry, an odd number of wavelengths divided by 2. And that's the condition for destructive interference, and this is something that we will have to remember when we start looking at interference by 2 slits, which is what we're going to do in a second. So before we start, I'd like to talk a little bit about these 2 gentlemen, Thomas Young, and of course you know this guy, Isaac Newton. Turns out that Newton, apart from discovering his laws and the law of gravity and all that stuff, apart from that, he also studied light. And his theory was that light was made of little balls, little particles. And then what he said, it was like, well, for each different color, you just get a different type of ball, right? So when so for example, imagine I have a plant, here's my plant, oops, here's my plant. Alright, and then my plant will absorb some of these balls, some of them will bounce back, and then that explains why some things have some colors. And then in a mirror, well, it's really easy to explain why mirrors reflect things, because, again, these are just balls, right? And we know, because of momentum conservation, that if a ball bounces on a mirror this way, it's going to bounce up at the same angle. And that's exactly what light rays do. So, to him, clearly, light had to be made of particles, which is ironically what we believe nowadays. And this theory had some problems. So, for example, refraction couldn't really be explained very well. So Newton was like, well, there is some kind of force in the material that deviates the particles. But like why or how, that wasn't explained. Then a while later, and by a while I mean 100 years later, I think, even more, this man, Thomas Young, believed that light was actually made of waves and not particles. And he decided to go about proving. And in order to do so, he was like, well, what kind of things do waves do? Well, one thing that waves do is interfere, right? So if I have a little wall with 2 openings and these are water waves, then what's going to happen is that this is going to create ripples, and then these ripples are going to interfere, and I'm going to be able to see an interference pattern. And I can then later on look, for example, if I have a little screen here, I can be like, okay, so here I'm going to see some places will have really big wave, some of them will have no wave, and so on. And we call this an interference pattern. So what Young thought was like, well, if light is a wave, I should be able to see an interference pattern. And maybe the fact that I'm not seeing one is just that its wavelength is too little to actually see when the openings are very big. So for example, when there's 2 windows, we never see interference patterns of light, right? We just see shadows. Through a door, we don't see light diffraction. Again, we just see shadows. So light does seem to behave like little balls. So I thought, what if I make the opening and the separation small enough? And that's what he did. And he did it like in the crappiest way possible, which was with a candle. And then you can also do that with sunlight. And in class, we will do this with a laser. So he had a candle here, and then he had this little piece of paper with a little pin, like a little hole here made with a pin. And then he used a card, like, the card that you use for playing card games, and put it in the middle. to split the beam. And on the wall, he observed interference patterns, and that's how he convinced everybody that light was made of waves. And it wasn't easy, because for everybody, Newton was like a god. You don't touch Newton. So it took a lot of convincing for people to start believing that light was a wave, because Newton was untouchable. I mean, for good reason, but yeah. Now, this is all well and good, to look at these little drawings and to figure out what he did, but now we need to do the math. So what I'm going to do is show you a little diagram of his experiment, and we're going to try to deduce what one is supposed to observe on the screen. And it is not going to be easy. So again, we assume that we have some plane waves coming here, which means just some, we have a source of light that's very, very far away, so that the wavefronts are pretty much parallel to the screen that's coming here. Doesn't really matter. Once it gets here, what's going to happen is that each one of these little slits that we're going to assume to be infinitely small are going to start emitting wavefronts like this. Finally, each one of these wavefronts is going to touch the screen. This one and this one will be at the same place, and therefore they will interfere. We need to figure out the type of interference that we see at each point on the screen. So for example, we have here one ray coming this way, one ray coming this way. Well, they're supposed to meet here, but I can't draw. And you can see that this length is smaller than this length. Therefore, there's a path difference. And remember, if the path difference is a multiple of half lambda, then we're going to get destructive interference. If the path difference is a multiple of lambda, the wavelength, we're going to get constructive interference. Now let's get to this. Now, in order to deduce this, we're going to have to do several things which are questionable, but that we do very often in physics. The first thing that we're going to do is we're going to assume that this screen is infinitely far. Why? Well, because then we can say that these two rays are approximately parallel. And if this is infinitely far, then these two angles are pretty much the same, because they have to bounce on a screen that's really, really, really far away. Okay. Now, apart from this, because these two rays are actually parallel, we can actually just take a look at one angle, which is really this angle between the middle of the screen and here, that we're going to call theta. So let me just show you what I mean by that. So this goes here, this is the normal, and we're taking a look at this angle here. We're going to call it theta. And also we need to take into account that the separation between these two guys is d. Now I need to redraw this thing to show that these guys are really parallel. So let me do this. I'm going to zoom out and try to do this on the other side. So if I redraw this with these two guys being parallel, I have this thing, I have the opening and another opening, and then I don't show the screen because it's infinitely far away. And then what I have is two rays. One goes this way and the other one goes this way, and they both bounce on the screen somewhere there. And remember, here I have this angle theta, which is the angle that both of these guys do with the normal to the screen. Okay, so then I'm like, well, what will be the difference in path of these guys? Well, obviously, most of this will be the same as most of this. So the only difference really is this tiny little bit here. So what I can do is I draw a perpendicular line from here to here. Let's just draw it like that. Okay, well, that is supposed to be perpendicular. And really, then this and all that will be exactly the same length. The only difference between these two paths is this part here. And the beauty of this is that because this angle here is also theta, then this is 90, and then this has to be theta too. So this angle here is theta. If you don't believe me, get a piece of paper and prove it to yourself. Okay, so now we have this angle theta. Now it's obvious that this thing here is the hypotenuse because these two things are perpendicular, and we want to know this place here. So D is the hypotenuse, and we want to know the path difference, which is this side here, which is the opposite side. Now, please tell me out loud how we get the opposite side if we know D and we know theta. Okay, I really hope that you said the sine. So the path difference is going to be D sine theta. Cool. Easy peasy. Okay, now we need to take this result and keep it in our memory in order to deduce the rest of this thing. So I'm going to zoom out a lot. And let's see if we remember this. So the path difference was D sine theta. Now what we need to do, what we're really interested in, is the distance between two consecutive maxima. So remember that we have here our screen, and here's, well, actually the screen, the wall, here's our screen, and from this point here, so here this, the middle of our thing, and we are interested really in knowing how far the next maximum is. So let's call this Sn, and this means the distance to the maximum of number n. So we have first maximum, then maximum number 1, 2, 3, 4, and so on. Okay? Now remember that this angle is equal to this angle and is equal to this angle because we're saying that this screen is infinitely far. So basically we just care about this angle here. This is theta. And now we're going to use the fact that because this is very big compared to this, theta is really small. And because theta is really small, we can do what we did in the last video, which was using the fact that sine of theta is more or less equal to the tangent of theta, and it's more or less equal to theta. Cool. So instead of writing sine of theta, what I'm going to write is just the tangent of theta, which is just this divided by this. And then I'm going to call this distance between the wall and the screen big D. So then we have that the path difference is just D times the height of the maximum number n, and then divided by big D. Cool. We're almost there. Now what we need to remember is that when the path difference is n times lambda, then we have a maximum. We have constructive interference. So I can rephrase this as n lambda equals d Sn over d. So this tells me when I find a maximum. Anytime that this times this distance over d equals n lambda, I'm going to have a maximum. I can rearrange this, of course, and please don't ask me for help about how to rearrange this because we should know how to do this already. We should have n lambda big D over small d. And that's the position of the nth maximum. But we actually don't care about this. What we really care about is the distance between two consecutive maxima. So what is the distance here between Sn and the next one, Sn plus 1? Okay, so let's see. So what we really want to know is Sn plus 1 minus Sn, which will be equal to n plus 1 lambda d over small d minus n lambda d over small d. And this is just because n plus 1, so instead of n, I write n plus 1. And for n, I just write n. And I just subtract these two, and then I'll have the distance between this guy and the next. Good. And as you can see, the n and the n are going to cross out. So I'm just going to be left with gamma d over d. And this is the distance between two consecutive maxima. So, and this is very important because this means that if I do an experiment, for example, the one with the card that we're going to do, and I look at the separation between two maxima, and I know the distance to the wall, and I know that the separation between the two slits, then I can find out the wavelength of whatever it is that I'm looking at. So this will enable us to find out the wavelength of the laser that we're using. And this not only proves that the laser is a wave, but it also tells us which wavelength it has, which is a very important information, because if the wavelength is very small, that explains why, for example, there's no diffraction through big apertures like a window. That is what Young did, and that's what we're going to do in class next day. Now, if you thought that was hard, brace yourselves, because now we're going to do this an infinite number of times. So now we're going to talk about the pattern that we see on a screen, when instead of having two slits, we just have an opening. But the opening is not infinitely small. It has a certain width b. So we have some wave coming this way, and then the wave just, diffracts through the opening, and then there's a certain pattern that we will see here. So what happens in here? Well, instead of thinking about this as just a whole wave going through here, what we need to think about is that each of these points is really emitting its own wave. And when you take the wave that comes from one of these points, you can look at the path that it takes to get to a certain point, and then you can take a look at some other part of the wave and take a look at the path that it takes to get to a certain point, and then you can look at the path difference between these 2 points, and then you can figure out whether there's constructive or destructive interference. And of course you'll think, well, yeah, but that's a lot of work, right? Because we can separate this into an infinite amount of little rays that come out of here, right? So how are we going to do this? And of course, the actual way to do this is using calculus, which allows us to add up an infinite amount of things. But in this case, we're going to do a much dirtier trick, which consists simply in splitting this into 2. So what I'm going to do is let's take, for example, this point here at the very start, and compare it to this point here. And let's say that these 2 guys emit some ray that goes up right there to the wall where they interfere. And I'm going to do the same thing that I did the other day, and by the other day I mean in the last slide, and say that this angle theta is the same as this angle theta, because this is really, really, really far away that way. So same thing we did for interference. And then I'm like, well, imagine that these 2 guys interfere constructively, for example. Well, if these 2 guys interfere constructively, then the guys right below are also going to interfere constructively, because they have the same path difference, and it's the same angle, because remember that the angle is the same for this, and therefore it's the same for this, and this, and this, and this, and this. So what I can do is 2 by 2, I'm like, well, then if I know that these 2 interfere constructively, then so do any other pair from here to here. And therefore I can assure myself that this whole thing will have constructive interference at that point. So just by looking at these 2 rays, I can basically figure out what the whole thing is going to do, which is great, because if I had to do the whole thing, I would go nuts. Okay, so now I'm like, okay, good. So I need to draw myself again what I did before, which is these 2 looking parallel at a certain angle theta, right? So let's do this again. Let's zoom out, and we've got our diffraction opening. This distance is b, and then we have one guy going this way, one guy going this way. This is b halves, and then again I make a perpendicular from here to here, and this little part here is the path difference. So I make this perpendicular here, and this here is the path difference, and of course this here, which is b halves, is the hypotenuse. So just like before, I say that the path difference is equal to b halves times sine of theta. But in this case, I'm really lucky again, because this is a small angle, so I can say that this is more or less equal to b halves times theta. Now, in this case, we're not really interested in the distance between any 2 maxima, because what really happens in an interference pattern, in diffraction, is that we will have something like this. We'll have a big maximum here, and then small minima like this. So what we are normally interested in is the width of the first diffraction maximum. Now, in order to do this, we need to remember when there's destructive interference. So this distance here, let's call it S, is going to be equal, well actually this is really S halves, right? Because I really want the width of the whole thing, so this whole thing. So this distance here is going to be half the width of the first diffraction minimum, which is what I want. And we know that here there has to be destructive interference, and there's destructive interference when the path difference is a multiple of lambda halves. In this case, this is the first maximum, so the path difference has to be exactly the wavelength over 2. So therefore, I go over down there, and I just say that the wavelength over 2 has to be equal to b over 2 times theta. And therefore, theta has to be equal to the wavelength over the opening. And that's it, I'm done. So the idea, this is called the angular width. It just tells us at which angle I'm going to get the first minimum of interference. And if you look at this formula, it really fits our common sense. Remember that I told you that if the wavelength is very small, then there's very little diffraction. And indeed, if this is very small, then this angle is very small, so 1 point looks like 1 point pretty much. And if b is very small, then this gets very big, and therefore I get a lot of diffraction, so this thing gets really spread out. So this is what we would reasonably expect just by understanding how diffraction works more or less. Now, we also need to know that this only works for a square opening, and for a circular opening things are a little bit more complicated and you need to use calculus and whatnot. So you just have to know, and it's in your data booklet, that in that case theta gets multiplied by 1.22. So it's exactly the same result by times 1, but times 1.22. And again, it's in your data booklet. All you need to say is like, okay, is it a circular opening? Then this goes. Is it a rectangular opening? Then this goes. These are approximate results anyway, so it doesn't really matter which one you use, but sometimes in the IB they want you to use this when it's circular. I really feel for you guys. This video is hard and long, but there's nothing much I can do about this. We will go over this in class, so don't panic. So what if now I have interference because there's 2 slits, but the slits do not have infinitely small sides, but actually have a certain size? What's going to happen? Well, in this case, you could calculate what's going to happen, but I do not recommend it. What's going to happen is that we're going to get a combination. So first thing I'm going to do in blue, the interference pattern. Remember that the interference pattern looks something like this. Right? So black, white, black, white, black, white, whatever. So we will have something like this. At the same time, we're going to see a diffraction pattern because each one of these slits is, has a certain width, and therefore there's some diffraction. So the diffraction pattern, remember, looks something like this. Of course, we can't have both at the same time. So what are we going to have? Well, what we're going to have is something that we call a modulated signal, which means that we're going to see an interference pattern that has the shape of a diffraction pattern. So let me show you what I mean. Here's my pattern. So what I'm going to do is I'm going to draw first the shape of the interference pattern as a dotted line, because it's not really there. I'm just imagining it. Okay, so here's my diffraction pattern. Okay, and then what happens is that I have an interference pattern just like this one that will follow this dotted line. So something like this. Okay, well, this is probably pretty bad, but you get the idea. The basic idea is that the interference pattern will have a maximum height that is determined by the shape of the diffraction pattern. So we will have a combination of diffraction and interference patterns at the same time. And just because I can draw, I'm showing you two extra pictures that pretty much show the same as this thing here. So here you can see this is the interference pattern. You can see that all maxima are equally spaced, and then this is the diffraction pattern. And you can see how the interference pattern is modulated by the diffraction pattern. So you can see like the overall pattern is of course the diffraction pattern, but then the black and white stripes are going to be determined by the interference pattern. And the way that this actually looks in reality, so this would be a typical diffraction pattern. So this is the first the first two minima and then the thing in between. And here is what happens when I add another slit. So I get an interference pattern modulated by a diffraction pattern. Again, so this would be first maximum, then second maximum, and third maximum, and so on. But our suffering is not over yet, because now we need to talk about what happens when we have diffraction through multiple slits. So instead of 2, what happens if we have 3 or 4 or 5 or 7 or 25? So first what we're going to do is that we're going to look at this picture and try to figure out what's going on, and then later on I'm going to show you a graph that will make it much clearer. So as you can see, in 2 slits what we have is basically, again, our regular diffraction pattern that depends on the width of the slits, and then we just have some maxima, so maxima, 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 maxima. If we look at 3 slits, you can see that we still have something similar, but the maxima are not the same. Some seem to be higher than others, right? So this looks to be a lot brighter than this one here. So it's as if another secondary maximum had appeared between the primary maxima. So we have a primary maximum, then a secondary one, then a primary one, then a secondary one, then a primary one, and so on. So between each primary maximum, there is a secondary maximum. And why does that happen? Well, if you think about it, the idea is that now we have 3 slits, right? So what can happen, in a very basic way, is that because we have 3 waves coming, we can either have the 3 together interfering constructively. That would be one of these big maxima, but we could have, for example, only 2 of them interfering constructively and the other one not. And then we would have a maximum that is smaller. Of course, as we add more and more slits, what's going to happen is that we will have more and more possibilities. So we will have either all interfering constructively, and then we will have a really big maximum, and then we will have lots of smaller possibilities for when these guys interfere constructively 2 by 2 or 3 by 3. And indeed, if we look at 4 slits, that's what's happening. Now we have 2 secondary maxima for each primary maxima. And if we go to 5 slits, we still have 3 for each, but they're very, very hard to see. There's 3 of them, but they're very, very little. So what happens is that this little maxima gets smaller and smaller and smaller and matter less and less and less, until only the primary ones matter. And if you look at it, see, all the primary ones are located at the same point. So if you look at the 2-slit interference and at the 7-slit interference, you see all of these are maxima, 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 and maxima. So the only thing that changes is that between these 2 guys, there will be a bunch of secondary maxima that become less and less important as we make the number of slits bigger. So for 2 slits we don't have secondary maxima, for 3 slits we have 1, for 4 slits we have 2, for 5 slits we have 3, 7 slits we have 4, but they're almost invisible, and so on and so on and so on. Now let me just show you a little graph showing this situation, but the idea is pretty much the same. So again, for n slits, it works just like for 2 slits. It's just that we get secondary maxima in between, and these maxima get less and less important, and the more slits that we have, the more maxima that we have. Okay, so let me show you the other picture. Okay, so here's the other picture, and you can see, again, that at the beginning we just have primary maxima, that then later on we have primary maxima followed by a secondary maxima, then primary maxima followed by a bunch of secondary maxima. Careful, here's 6 slits. And then as the slits go like more and more and more, the maxima gets narrower and the secondary maxima get smaller and smaller and smaller until they're almost invisible. So basically for an infinite amount of slits, what you would get is something like this, just a line. And then everything else would just be flat. So you would have perfectly thin line here, perfectly thin line here, perfectly thin line here, and all these other secondary maxima would just disappear. It's just the logical evolution of this. Okay, so now we're going to talk about something called the diffraction grating, which is basically a limiting case of this thing. So diffraction grating, you can consider it as an interference setup with an infinite amount of slits. So just as many as you can imagine. And each slit is very, very, very thin. So thin that there is no diffraction pattern. So basically we're talking about all these maxima here would have the same height because there would be no diffraction pattern over them. So what would we get then? Well, we would get the same thing that we get in a regular interference pattern. It's just that, remember, the primary maxima would be infinitely thin because we have an infinite number of openings. And the secondary maxima would just be non-existent. So as I told you before, we would have something like this. But in this case, all our lines would have the same height because there's no diffraction pattern to modulate them. And just like in the regular interference pattern, the condition to have a maximum is given by the constructive interference condition, which is d sine theta equals n lambda. So remember, when the path difference is a multiple of lambda, we have constructive interference. Of course, the destructive interference would be right in the middle. This is a very, very handy device because, as you can see, the position of this maxima depend on the wavelength. So if we have several wavelengths going through a diffraction grating, what's going to happen is that the maxima are going to end up in different points and are going to be very, very thin. So we're going to be able to distinguish between all the different wavelengths because they're going to end up in different spots. And this allows us to take lights that's a mix of colors that we don't know and separate it into its constituent wavelengths. And that's, for example, what we're using when we're analyzing the light from gases and trying to determine their spectrum, which is what we did in atomic physics not very long ago. Okay, and this is just because I'm guessing that you guys must be very, very tired right now. So here's SpongeBob. Have fun. Okay, I promise this is the last thing. Really. There was going to be more in this video, but I decided to cut it because it's too much. Anyway, the last thing that we're going to look at is called thin film interference. And this is what we see sometimes, for example, in a soap bubble. You see that there's many different colors when you look at it. Or if you look at, in this case, this is a really thin sheet of oil on water. And then you can see that you get these really weird colored fringes. And this is something that most people had no idea why it was happening for many, many years. And it's something that you can actually explain using some really simple interference laws. So let's see how this works. So the basic idea is that you have this really thin film of oil, soap, something like that, and there is some light that's coming in, and part of it is reflecting, and part of it is being refracted, then reflected in here, and then being refracted back. And these two rays, because they're parallel, they're going to interfere at some point at infinity. And at infinity, remember, it just means, far enough. So that when we look at them, these two, we will either get a maximum or a minimum of interference. Now, in order to deduce what happens here, first we need to know a rule that is related to, well, do you guys remember when we were doing waves on a string? So we had a string like this, a wave in a string like this, and then we had this little rod here, and we tied the string to the rod. And what happens was that if this was tight, if this was a tight knot, what would happen is that the wave would reflect off, but it would be opposite. So you would have something like it would be coming up as a crest, and it would be coming back as a trough. So basically it was gaining a phase difference of pi. Remember that a phase difference just means this is 0 angle, this is pi, this is 2 pi, or you can say it gained a path difference of lambda halves. So basically by reflecting off here, we had to add a phase difference of pi or a path difference of half a wavelength. And this also happened when we had some thin rope going onto a thick rope, and again we had that the wave would go from here and then reflect with a phase difference of pi or a path difference of half a wavelength. So in here something very, very similar happens. When light is going from a medium with lower N, like air, to a medium of higher N, like soap or oil, what happens is that on reflecting here, it gains an extra phase difference of pi or an extra path difference of lambda halves. So in here, in this boundary, the phase difference goes up by half a wavelength. But this does not happen in here. This is like a thick rope going to a thin rope. When it reflects, nothing happens. We just have, the wave just continues. So therefore we have two waves that are interfering, and their path difference is, of course, all this, because this wave here has traveled this more than this one, and then we need to add lambda halves, because this guy has gained a path difference of lambda half when going from here to here. So now that we know this, we can figure out when there's going to be constructive interference between this guy and this guy. So the idea is that normally there's constructive interference when the path difference is equal to n times lambda, where lambda is the wavelength. But in this case, if the path difference is n times lambda, we still have an extra lambda halves from the fact that this guy is reflecting here. So this path difference is really going to be this much, and then we need to add lambda halves, right? So plus lambda halves because of the reflection. Therefore, if we put this together, we really get n plus 1/2 of lambda. Now normally this is the condition for destructive interference, but in our case this is a condition for constructive interference, because remember, this would give us constructive interference if there wasn't any reflection here, but because there is one, we need to add 1/2 here. Okay, so we will get constructive interference every time that the path difference is this much. Now, what I'm going to do though is, instead of using n as a natural number, I'm going to use m. And the reason for this is that we're going to be talking about the refractive index of this thing, and you know that this refractive index is called n. So in order to not get confused between the refractive index and a natural number, which is 1, 2, 3, 4, 5, I'm going to call this m so that there's no confusion. So every time that the path difference is some natural number plus 1/2 times lambda, we're going to have constructive interference. Now, we need to see what the path difference actually is. And in order to do this, we just need to look at the path of these two things. So the path difference is really the distance between here and here. Now, the first thing that we need to do is, again, be a little dirty and say, we're going to assume that this angle is really little. So little that really the path difference is just 2d. So the path difference is just 2d. And we will have constructive interference every time that 2d equals n plus 1/2 of lambda. So equals n plus 1/2 of lambda. But now we have a problem, because lambda here, the wavelength here, is actually not the same as the wavelength here. In fact, it is relatively easy to prove, and I will leave this to you as an exercise, that the wavelength inside the oil is the wavelength in air divided by n. So this should be divided by n if we want to do things properly. And of course, I don't like the way this looks, so I'm going to put the n over here. So simply I will get that 2dn equals m plus 1/2 lambda over, no, not over n, because I already put the n on the other side. So this is the condition for constructive interference of these two rays that are coming out. Now, of course, if this is the formula for constructive interference, it's relatively easy to find the formula for destructive interference, right? Which is just going to be exactly the same, but I just need to get rid of this 1/2 here. So if I want, so this is constructive, and if I want destructive, I just have 2dn equals m lambda. And this will give me the condition for destructive interference. And that's it. Now we're finally done. Okay, so we came to the end of the video, and let's see if we have done what we were supposed to do. I didn't show you the objectives at the beginning, but this is what the IB wants you to know. So first thing, we applied this principle of superposition to derive the interference of light from two thin slits. We did that. Then we deduced the diffraction pattern of one aperture using what we learned in this example before. Then we deduce how the diffraction would modulate the interference pattern of two slits. Remember that we had there was the diffraction pattern, and then the other one followed that pattern. And then finally, we deduce what happens when you have multiple slits and a diffraction grating, which is just lots of slits put together. And we just did this, the interference pattern of a thin film, which is maybe the hardest part, and I will make you reduce it in class. So I hope this wasn't too hard, which it probably was. If you had difficulties with this, don't worry too much. We will go through this in class, and we will do this a lot more slowly. So I'll see you in class. Bye, guys.